lectures. So in this session we'll be discussing the concept of vector triple product. We shall begin with the term vector triple product, that what exactly it means, followed by the various properties as well as questions. So let's begin. Okay, so the next topic that we have is vector triple product. As we discussed scalar triple product, now it's vector triple product. The vector triple product of three vectors A, B and C is defined as A cross B cross C. B cross C is in brackets. First of all you'll find B cross C, then we'll find the cross product of A with that resultant vector. If at least one of A, B and C is a zero vector, or B and C are collinear vectors, or A is perpendicular to both B and C, only then will this product turn out to be a zero vector. In all other cases, this product will be a non-zero vector in the plane of non-collinear vectors and perpendicular to the vector A. This just means that vector triple product, we are having three vectors and we are finding out the triple product, so therefore it is called as vector triple product, and this product will turn out to be a zero vector only in these situations: when one of A, B or C is a zero vector. This is 1. If one of ABC is a zero vector, then this will turn out to be a zero vector. This product will turn out to be a zero vector. Or B and C are collinear vectors, right? B and C are collinear vectors. Or third situation is A is perpendicular to both B and C. In all other situations, this product will not turn out to be a zero vector ever, right? So this was vector triple product. We'll be discussing some properties also, and then we'll be switching to some examples also based on these concepts, that is scalar triple product and vector triple product. Now we have the reciprocal system of vectors. If ABC be any three non-coplanar vectors, so that the scalar triple product of ABC is non-zero, then the three vectors A dash, B dash, C dash, defined by the equations A dash is B cross C by scalar triple product of ABC, B dash is C cross A divided by scalar triple product of ABC, and C dash is A cross B divided by scalar triple product of ABC, are called the reciprocal system of vectors to the given vectors A, B and C. So if ABC are given to be three non-coplanar vectors, moreover the scalar triple product of ABC is non-zero, then the vectors defined by this are known as the reciprocal system of vectors to the vectors A, B and C. Now we have certain properties based on these concepts. The first one says A into A dash, that is the reciprocal system as we have just now discussed. This product is 1. Okay. And next one says the scalar product of any vector of one system with a vector of other system that does not correspond to it is 0. Does not correspond to it means if we are taking the x coordinate A, then there we are taking B or C, not A dash, sorry, we are taking B dash or C dash, not A dash. So the product of A vector with B dash, or A with C dash, or B with A dash, that is not two corresponding terms, then this product always turns out to be product, that means dot product turns out to be a 0. Then scalar triple product of ABC with the reciprocal system, scalar triple product of reciprocal system is 1. I dash is I, J dash is J, K dash is K. Then if A dash, B dash, C dash is reciprocal system of scalar ABC, and R is any vector. Okay, if A dash, B dash, C dash is reciprocal system of, this is ABC vectors, A dash, B dash, C dash is reciprocal system of ABC, and R is any vector, then R can be written as R dot A dash plus R dot B dash plus R dot C dash. Or Either way, you can write it either way, or you can write R as R dot A dash A plus R dot B dash B plus R dot C dash C. Okay, now we have a question based on these concepts, that is scalar triple product, vector triple product and reciprocal system. Prove that the formula for the volume V of a tetrahedron in terms of lengths A, B and C of three concurrent edges and their mutual inclinations phi, theta and psi is given by V square is A square, B square, C square by 36 and this quantity. Okay, so how do we proceed in this question? If you remember, we have already discussed the properties, the formula for finding out the volume of tetrahedron, etc. So this question in fact is quite simple. I begin with let OABC be the tetrahedron. Let OABC be the tetrahedron with O as origin, and further let ABC be the position vectors of ABC, right? ABC be the position vectors of ABC. Then V we have already discussed in properties is equal to 1 by 6 scalar triple product of A, B, C. Okay, for that we have to assume ABC also. So let us suppose A is A1I plus A2J plus A3K. B is B1I plus B2J plus B3K. And C is C1I plus C2J plus C3K. Right? B is B1I plus B2J plus B3K and C is C1I plus C2J plus C3K. Now this is the formula, so we'll just substitute the values in this and we'll get the desired result. So V is 1 by 6 scalar triple product ABC, that is equal to 1 by 6. If you remember the formula we had also discussed, this can be written as simply the components of A, B and C. So A1, A2, A3, then we have B1, B2, B3 and then I have C1, C2, C3. V square can be written as 1 by 36 since we are required to find out the value of V square. So V square can be written as 1 by 36 into A1, A2, A3, B1, B2, B3, C1, C2, C3 and again we'll have A1, A2, A3, B1, B2, B3, C1, C2, C3. So this is 1 by 36 remains as it is. Then I have A1 square plus A2 square plus A3 square. Then I have A1 B1 plus A2 B2 plus A3 B3. Then I have A1 C1 plus A2 C2 plus A3 C3. The second component becomes, okay, let me write it down here, 1 by 36. This is A1 square plus A2 square plus A3 square. Then we have A1 B1 plus A2 B2 plus A3 B3. Then I have A1 C1 plus A2 C2 plus A3 C3. Here I'll get A1 B1 plus A2 B2 plus A3 B3. Then B1 square plus B2 square plus B3 square. Then B1 C1 plus B2 C2 plus B3 C3. And the third one is A1 C1 plus A2 C2 plus A3 C3. Then B1 C1 plus B2 C2 plus B3 C3 and C1 square plus C2 square plus C3 square, this determinant, right? So this becomes 1 by 36 into you can write it as this, and just in order to find out what, just in order to prove what is given in the question, we'll apply the formula for dot product. This can be written as A dot C. Now this becomes A dot B. Similarly, this is and B dot C, and this term is A dot C, B dot C, and C square. So this can be written as, okay, I'll first erase this. I'll continue here now. Now this can be written as 1 by 36, and I have A square, then I have AB cos phi, and then I have CA cos psi, then I have AB cos phi and B square BC cos theta. On the basis of what's given information, that is the angles between these vectors are given to be phi, theta and psi. On the basis of that, you can write it like this. Then we have CA cos psi, then I have BC cos theta, and then I have C square. This can be written as, I can take out A square, B square, C square common, so that I have 1 A square, B square, C square I have taken out common, so I have 1 cos phi cos psi, then I have cos phi, 1 cos theta, and then I have cos psi cos theta 1. Is this what is given in the question? Let us check. So this is cos phi 1, cos theta, cos psi, cos theta 1. So yes, we have reached the desired conclusion that the value of volume is A square, B square, C square by 36 into this. So the question was a bit lengthy because it involved certain calculations, not lengthy as such, but it was quite simple based on direct application of the formula. The next question that we have is, it is given that X is B cross C by triple product, scalar triple product ABC, Y is C cross A by scalar triple product ABC, and Z is A cross B by scalar triple product ABC. Where ABC are non-coplanar vectors, show that XYZ also form a non-coplanar system. First of all, we need to prove that it also forms a non-coplanar system. Then we need to find out the value of X dot A plus B plus Y dot B plus C plus Z dot C plus A. Okay, firstly we'll prove this, then we need to find out the value of this term. So, given that X is B cross C by A, B, C, and Y is C cross A by A, B, C, Z is A cross B by A, B, C. This is the given condition, and ABC are non-coplanar vectors. Since, what does this imply? This is how the properties get utilized. Since we have already discussed the condition of non-coplanar vectors or coplanar vectors, that then our ABC, what is the relation between scalar triple product and coplanarity or non-coplanarity. So since ABC are non-coplanar vectors, so scalar triple product of ABC is non-zero. Because if they are coplanar, if that was if and only if condition, and if they are coplanar, then scalar triple product is 0. So this is non-zero. So we need to prove that XYZ form a non-coplanar system. So we need to prove that the scalar triple product should come out to be non-zero. This was also ABC, right? This is what we need to prove. So for that, what we'll have let us first write down the scalar triple product of x, y, z. That will be equal to b cross c dot c cross a dot a cross b. So we have b cross c dot c cross a cross b by, we'll have scalar triple product a b c q. That will be equal to a b c square by a b c cube, which is equal to a b c, and that is obviously non-zero. We have already discussed that scalar triple product of ABC is non-zero because they are non-coplanar. So therefore this also comes out to be non-zero, which implies that x, y, z are non-coplanar. So x, y, z are also non-coplanar. We have proved. This was the first thing that we were required to prove. Next we have to find out the value of x dot a plus b plus y dot b plus c plus z dot c plus a. This is what we were required to prove. Find out x dot a plus b plus y dot b plus c dot z dot c plus a. Okay. So now what will we do? That this would be equal to putting the values of x, y, z in the above equation. In this equation we will just substitute the values of x, y, z. So the values of x, y, z were p cross c x was b cross c by triple product, scalar triple product ABC. So we have b cross c dot a plus b by scalar triple product ABC. Then plus y was c cross a. Then we have dot product b plus c by ABC. Then we have z was, okay, this was plus, z was a cross b dot c plus a by a b c. Okay, so we need to compute this. So this would be equal to b cross c dot a plus b cross c dot b. B cross c dot a plus b cross c dot b, upon it will remain same, a b c. Similarly this would be c cross a dot b plus c cross a dot c plus a cross b dot c plus a cross b dot a, and again upon it will be a b c, a b c, right? This is what we have. And after this, further, this would be equal to a dot, okay, this we have reached this. Now further this can be written as a dot b cross c plus, it will be a 0, and upon scalar triple product ABC plus b dot c cross a, again the same term, plus a 0 plus, so this is what we get after solving out this, right? So this further again can be written as ABC by ABC plus ABC by ABC plus ABC by ABC. So this is 1 plus 1 plus 1, so this is 3. So the value of the required term is 3. So again what we have done is we have just simply simplified the terms using the properties of dot and cross product. But again I am repeating, do not get confused in the properties, just practice a very good number of questions so that you get to know how do you need to proceed in case of dot product and cross product, what are the various properties, how are they utilized and applied in questions, so that you can easily solve out the questions. Okay, let us discuss one more question based on vector triple product. Let me take any question, say example 3. For any vector A, suppose, prove that A cross I plus J cross A cross J plus K cross A cross K is equal to twice of vector A. Let us solve this question, right? So how do I proceed in this question? For any vector A, this is prove that this is equal to twice of vector A. Let us take what is given. We'll begin with that only. We need to find out the values. We need to find out the value of this. In fact, we need to prove this is equal to twice of A. So this term is J cross A cross J plus K cross A cross K, right? This is the given thing, or we are proceeding from this term. This will try to prove to be equal to 2A. So this is equal to, now if you remember, A cross B cross C, vector triple product, this can also be written as A dot C minus A dot C into B minus A dot B into C, right? So we'll be utilizing this formula here basically. So we have I cross, now this is A, this is my B, this is my C. So A dot C into B minus A dot B into C. This is what I get from the first term. Let us enclose it within brackets. Then I have A dot C into B minus A dot B into C, right? Then what about this one? This will give me A dot C into B minus A dot B into C. This is what I get. So this would be equal to, now I dot I, J dot J and K dot K. These all terms would be equal to 1. This term, this term, this term. So this becomes A vector minus I dot A into I, right? Plus again a vector, and I have J dot A into J plus A vector, plus A vector, this was minus, plus A vector minus K dot A into K. This is what we have derived. I dot I, J dot J, okay, I'll write it down. I into I equal to J into J equal to K into K is 1. Right? This is equal to 1. We have utilized this condition, so we have reached here. A minus this. Okay, let's club up all A. So we have 3A minus, I'll take this also common, I dot A into I, plus I have J dot A into J, then I have K dot A into K. This is what I have. Now let A is A1I plus A2J plus A3K. Let us assume that the vector A is this. Then IA would be equal to I into A1I plus A2J plus A3K, right? So this would be equal to A2I square, A1I square in fact. This would be equal to A1I square plus A2IJ I dot J plus A3I dot K, right? This is what you will get if you have A as this, and then I am trying to find out the value of IA. So this is this, okay. This will come out to be this. This is A1 I square plus A2 I dot J plus A3 I dot K, will get this. So this can be written as A1 into 1, obviously I square is 1. Then I have 0, 0. So this I get as A1. Similarly, on similar lines, I can say on the basis of this that if I try to find out J into A, I'll get it as A2, and K into A will come out to be A3. And therefore, my LHS reduces to, or I'll write it down here. Similarly, J into A would come out to be A2 and K into A would come out to be A3, and therefore my LHS becomes, it was 3A, you can see from this equation, 3A minus this quantity, and I into A I have obtained as A1. So that will be equal to minus of A1I plus A2J plus A3K. A1I plus A2J plus A3K is again A, and therefore this gives me 3A minus A, and that would come out to be 2A, which is the required RHS, and therefore this LHS, this term is equal to 2A. Hence we have reached the desired conclusion. And again, do practice a very good number of questions on dot products, cross products, scalar triple product, vector triple product, just so as to increase your speed and so that you don't get confused between all those properties. Well, I hope you must have understood the concept of vector triple product and the reciprocal system of vectors. In the next session, we'll be switching to the linear combination of vectors, which is again an interesting concept. So just stay tuned.